All right, so our limit problems. First thing we are going to do is check and see what x is approaching. If it's approaching a number, we're going to try plug it in first, and then one of our strategies if that didn't work. If it's approaching infinity or negative infinity, we need to think about end behavior of the function. Most of the functions you guys had last night, all three of these are fractions. These aren't really like rational functions. They kind of are. They're a little bit weird. But we can use our horizontal asymptote rules to help figure out what the end behavior is. So we're comparing the top and bottom. So for this first one, is it top heavy, bottom heavy, or equal? Equal. Let's see. We have 3x on the top as our leading term. What do we have on the bottom? Root 2x. Yeah, because that root 2 doesn't simplify to 2. So it would be root 2x. So they are equal. So I'm going to divide the coefficients, and I get 3 over root 2. I got lots of questions yesterday like, wait, when do I have to plug in to see if the sign is different? The truth is you can do it every time. You just don't have to do it certain times because we know the answer won't change. So, I mean, if it's going to positive infinity, it's not going to change anyways. This is the same problem except with negative infinity. So let's see how this one's different. You do have to plug in if it's a special case with one of these square roots. So if we plug in a negative, where are we plugging it into, first of all? The original problem. Do not plug it into this one. We plug it into this one. So what will I have on the top, positive or negative? Negative. What about on the bottom? Positive because it's squared. So that would give me negative 3 over root 2. Okay. You also have to plug it in if you get a top-heavy situation, if it's a slant asymptote. If it goes to 0, you don't have to plug it in because it's just 0. Top-heavy, you have to plug it in. And then if it's equal, it really just depends on if you have one of these weird situations. If this was the actual problem and I plugged in negative infinity, it's not going to change the answer. So that's why it's like you don't have to, but if you want to, it will still give you the right answer. All right, and then down here, what do we have? Top heavy, bottom heavy, or equal? Bottom heavy, because this is really x squared on the top, and that's x cubed, so that would go to 0. Remember, if you're rewriting the problem, it has to be mathematically equivalent to this. So if you have an equal sign, or if you rewrite the limit notation, then x squared plus 1 is not equivalent to this. They have the same end behavior, because if you look at the leading terms, that's the only thing that's really important, but they're not the same problem. Okay, this problem here, this is from a past AP exam. So I notice it says the limit as x approaches infinity, so I'm thinking end behavior. X to the k, if k is a positive integer. So I have no idea what number it is, but k is a number. So I'm thinking a polynomial type. Could be x squared, could be x to the millionth power. And then we have e to the x on the bottom. All right, so this is where you kind of have to think about it. The reason we have the horizontal asymptote rules is because we kind of think about which side, the numerator or the denominator, which one's bigger. So if the denominator is bigger, let's say I have 1 over 10. If I keep plugging in bigger numbers on the bottom, 100, 1,000, 10,000, what are we approaching? Like what number are we getting close to? 0. That's why when it's bottom heavy, it's getting closer to 0 because the denominator is getting bigger than the numerator is getting. So it's just getting closer and closer to 0. If we have top heavy, if I have switched these two, we know it's going to infinity. It's just getting bigger and bigger and bigger. And then if it's even, these two numbers are just become negligible at a certain point. So whatever the leading coefficients is what's happening. So I like to think about it as a race. So in this case, we need to think about which do you think would get bigger, a polynomial or an exponential? Who would win that race? Exponential is going to win the race. So that means it's bottom heavy. So what do you think the answer is? 0. Okay. All right, let's talk about continuity. You don't have to write down these questions. I have a few questions up here for us just to kind of talk about. And I think you guys already know some of these answers. What does it mean for a function to be continuous? Anyone explain in their own words what you think it means for a function to be continuous? It never ends. Okay. Continuous. Never. Anything else? No holes. Okay. Anything else? No asymptotes. Okay. Does it matter what kind of asymptote? Could a continuous function have a horizontal asymptote? Yeah, it could. Negative infinity to positive infinity, okay? All right, I already heard one of these answers, but what kinds of things make a function not continuous? I heard holes and I heard asymptotes, but I think we need to specify what type. Vertical asymptotes. What about slant asymptotes? Do those make it not continuous? Depends. Okay, so horizontal asymptotes just tell you where it's going at the ends. If it doesn't have a horizontal, it has a slant. So they act the same way. So you can cross over a slant asymptote and a horizontal, just not a vertical. So vertical asymptotes and holes. Anything else make a function not continuous? I can think of a graph we've done recently. What? Yeah, a piecewise function. Yes, where it jumps. Remember that absolute value of x over x, that graph? That's another one. Those are the three types of things we're going to be talking about. And then how can we use limits to describe a discontinuity? So there's three types we're going to talk about: holes, vertical asymptotes, and a jump. That one we just talked about. So I'm going to have you guys write down this definition of continuity first, and then we'll get into our limits. All right, so a function is continuous if the limit exists, the point exists, and they match up. So I'm going to draw a graph that will explain it in a second. But let's talk about our first type of discontinuity. It's called removable. A removable discontinuity means that the limit exists. I'm going to draw two different scenarios here. First, right here, we have a function. The limit exists, but the point doesn't. That's what that means right there. The other situation is the limit exists, but it doesn't equal where the point is. So like that. Both of those situations are a removable discontinuity. And we know the limit exists because both of these guys on either side are going to say that it occurs at the same value. But it does not. All right, the other type is non-removable. You guys already talked about the two different types we could see there. So we could have a vertical asymptote, or we could have a jump. And here we go, non-removable. The limit does not exist at either of these situations. A jump looks like this. An infinite, that's what this one is called, is where we've got a vertical asymptote. I'll just draw a little rational function here. You're going to have to justify on these ones how you know it's removable or non-removable. This is what we're going to be using as our justification for both of these. All right, ready? Let's do a problem. So we're going to use this one graph to answer these three questions. By the way, this is exactly what your homework looks like. So you're going to have the same three questions in your homework tonight. So first it says state the intervals on which the graph is continuous. Let's do that first. Oh, look, I think I'm highlighted. 1. Okay, so let's just go from left to right. Looks like it goes forever left, so we'll start with negative infinity. What's the first place you see a discontinuity? -4. Union, -4 to, what's the next place we have a discontinuity? -2. Union, -2 to what? 0. Union, 0 to 3. I'm not going to have enough room. Union, 3 to infinity. There we go. Okay, so all I'm doing is excluding the x values where it's not continuous. Number 2 says state and classify all discontinuities. So classify means tell me, is it non-removable or removable? You don't have to tell me if it's jump or infinite. Just those two categories is all you need to know. So 2, we're going to do this for each of the discontinuities and then justify using calculus. All right, so let's just go left to right. We said -4 was the first place. So at x equals -4, is that removable or non-removable? Removable. It says justify using calculus. So I'm going to go back a couple slides for just a second. So picture what this looks like. Not the whole. Okay. I go back to this one. Which situation does this look like? The first one or the second one? The first one. There was no extra point. So we're going to say that the limit exists, but the point doesn't. Here we go. Okay, so I'm going to say, oh, you know what? I don't think they named this graph. Let's just call it f of x. So I'm going to say the limit as x approaches -4 of f of x exists, but f of -4 does not exist. Okay, where's the next discontinuity? -2. All right, at x equals -2. What type is that one? Removable or non-removable? Non-removable. Okay, my justification for any non-removable is we just say the limit doesn't exist. I'm just going to say limit as x approaches -2 of f of x does not exist. I like those ones, there's less writing. Okay, next we have, I'm gonna need more space here, at x equals 0. All right, what type do we have at x equals 0? Yeah. Okay, so removable is like the limit exists. So right here, like they're both coming together at the same point, but there's a hole. But at -2, see how there's a whole jump? Like we got this here and this here. So that's what makes it non-removable. At x equals 0, which type is it? Removable. Okay, is this the same situation as the last one? This is the other situation because the point is there. So here's how we're going to write it. We're going to say the limit as x approaches 0 of f of x does not equal f of 0. Because there is a point there, it's just not equal to where the limit is. All right, and we've got one more. I'm going to write it over here. At x equals 3, what type do we have? Non-removable. And what's the justification for non-removable? The limit doesn't exist. The limit as x approaches 3 of f of x does not exist. All right, so we did 1 and 2. Now question number 3. If a removable discontinuity exists, how would you remove the discontinuity? We'll use a different color so it stands out. We'll do red. Okay, so we had 2 removables, right? One at -4, one at 0. So we're going to say what point would make this continuous? So at -4, what point is it? Yep, so I would just put f of -4 equals 0. That's what would make it continuous. What about at x equals 0? F of what? F of 0 equals -6. That's it. So on your homework, there's a blank for part C. If you didn't have any removables, you just leave it blank. You don't have to answer that question. Okay? I'm going to let you guys go ahead and start working. Let me know when you get to the back, because we might need to go over one of the sections. But I'll let you guys go ahead and get started.